Hi, I'm Josiah Kane, Director of Innovation at Sherwood Design Engineers. I'm here today with my colleague Ian McCrae and Weatherby Dorshow of Earth Analytics. We're going to share with you a workflow that we've been developing um, to marry GIS tools to complicated modeling tools for climate in urban environments. As we're all aware, heat and humidity are on the rise globally. And in response to climate change, we're looking at how urban fabric and cities might respond. Urban heat islands in cities are a problem globally. Cities tend to heat up significantly due to thermal mass and other factors that we'll get into. Heat waves have become rampant and cause problems for energy and water resources as well as human health. The challenge is that inherently, by the nature of their thermal mass and lack of vegetation and hydration, we've generally armored and drained the urban fabric. They are sources of heat and respond more acutely to climate change than natural environments. So we're investigating and trying to understand from an engineering standpoint how to model the significance of reintroducing some of the functionality that we get from green infrastructure and living systems in urban environments. There's other factors like permeability for water to be able to flow through permeable paving surfaces. We're also looking at air quality and things like humidity from evapotranspiration from plants. And these feed into a model that Ian will describe momentarily. This is extremely important from a mortality point of view. Surprisingly, in the United States, more people have died from heat waves in cities than from any other natural disaster, such as an earthquake, flood, hurricane, etc. So there is a strong motivation beyond just technical to normalize temperature in response to climate change. I'm going to hand it off to Ian on the modeling.
Hi, everyone. My name is Ian McCrae. I am an innovation designer with Sherwood Design Engineers and also an educator at UC Berkeley. I will be presenting on the modeling and quantification of ecosystem performance utilizing CFD platforms in order to evaluate microclimatic impacts. The value of this is that site-specific modeling, simulation, and analysis is really essential to understand a project site and surrounding context in a holistic fashion. And this accounts for the unique composition of spatial geometries, materials, and vegetation that can give rise to distinct microclimate and environmental patterns. We can essentially harness data-driven design to help quantify resource, economic, and community implications. The value of this is that while there's a wealth of research to help develop portfolios of design strategies to mitigate the negative impacts of climate change, no one strategy can be applied universally with the same assumed outcome, as seen here by the diverse array of city composition and street plans. Until recently, most CFD modeling efforts in industry have largely been building-centric, focusing on buildings' individual performance and really struggling to account for the broader context. And this includes topography and the shifting gradient of the constructed realm, moving from the suburbs to the urban core, all of which work together to influence unique environmental and meteorological patterns for a given community. Really, we're only as good as the data we use, so we should strive to utilize accurate site-specific data to inform our process so that we have reliable results to work with. And here's just an example of the array of data inputs that can inform a simulation. The nexus of these different factors also provides a suite of valuable information, which gives us the ability to evaluate alternative design proposals under current and projected climate conditions before a shovel ever hits the ground. This really allows for an iterative design process to help fine-tune and enhance site performance. There is great opportunity utilizing Esri tools in order to bring together different file sets to help build models that then go on to be simulated in a CFD environment. This is tree location and species type, building footprints and height, and really accounting for the broad composition of the urban realm, such as parks, parking lots, streetscapes, and water bodies. Another valuable application of the Esri platform is the ability to take the wealth of results that come out from looking at different strategies at different study sites under variable climatic conditions and doing batch analysis so that you can more rigorously generate statistical analysis in an efficient fashion that can help inform spatial applications. I'd like to provide an example of what this process can look like. We worked on a proposed community college campus in Palm Springs, California, and what you see here is the architecture and landscape concept design at an early stage of the process, which has since evolved, but nonetheless, it was a valuable exercise to see how this proposed idea performed within the local context. The project site was surrounded by a suburban matrix located near an airport. It's highly impervious with minimal vegetative coverage and is generally a hot and arid environment. Here is an example of a completed 3D model in order to simulate the proposed architecture and landscape design relative to the surrounding existing context. We were able to account for the location and species type of tree canopy, the architecture of the building, the surrounding ground plane materials being pervious soils, asphalt, and sidewalks. And then incorporating local meteorological data. For the purposes of this project, we wanted to see how the site performed under high temperature conditions. The average temperature in Palm Springs in July is 107 degrees Fahrenheit. So we pulled local data from the nearby airport and used that as an input parameter in order to drive the simulation. Then the results were fed into the Esri platform in order to be studied in a more rigorous fashion. And I'll hand it off to Weatherby to show you how that process took place.
Excellent. Thanks, Ian. I'm going to do a little demo here, dive into some data for the geeks. As they say, we land the geeks. We'll start right off with visualizing some outputs from the CFD modeling process. And some of you may be aware of new capabilities for visualizing and investigating voxel data sets, true three-dimensional data sets with volume in ArcGIS. Here we see this data set presented, and currently we're looking at mean radiant temp. And I actually modified this a little bit so that I can see the data I'm interested in. You can basically see that the original model, if I come up here, is some noise that I don't really want to see. And so we can kind of drill right down. And one of the things that's really interesting about this is the directionality of the values. The blue are the buildings themselves. And obviously we can drop in all the CAD data and what have you. I can also take these various slices and investigate them in different ways. So if I come in here and look at this from the top, I can then actually investigate that with a slider to drill down to some elevation at which we want to look at the implications. And along that, essentially things like evapotranspiration or each one of the variables, and some of which are displayed right here. We had some 3 million points that came out of the modeling software, and I'm just gonna switch back here. We used Kriging to develop basically to reformat some of that data into a net CDF using EBK 3D. And so here I'm going to take a look at another one of these variables. One of the really interesting things here is that obviously there's a workflow that that's going to allow us to look at not only, I'm just going to go back here and turn off these things. Okay, back it out. Okay, so not only can we take the outputs of this complex CFD modeling approach and visualize them, we can then quantify them and basically cut this into blocks and do spatial analysis on the results, right? So we can look at performance, we can look at certain zones of the site, and there's a lot of other ways that we might want to slice that up to visualize it, as well. But then, importantly, the workflow, Ian mentioned shapefiles. Well, as we develop this process, building sort of a pipeline to be able to feed data back into the models and thereby, automate this whole process. And the outputs, another thing that Ian mentioned was sort of the scenarios and the complexity of all that. We're looking at using the latest version of ArcGIS GeoPlanner to be able to present that information to stakeholders and let them comment on that. So there's a lot we can dig into here, but the point of the matter is that we can do the GWiz visualization, but we can also do really powerful analysis based on an already extremely sophisticated engineering CFD model.
Based on what we just showed you, what does this mean? Like, what are we actually able to do with this tool? Go ahead. We've basically taken climate change inputs, sort of captured those into specific risks in the environment, used computational fluid dynamic modeling to evaluate strategies and understand approaches, materiality, vegetation, geometry, and design form, and inform a design process to generate solutions that are climate resilient. So this provides us tremendous visibility into how some of these impacts might affect various design strategies and solutions. We can see this applied in projects like Brooklyn Bridge Park, where vegetation is being introduced. A Microsoft campus that's using vegetation on the roof as part of a strategy to maintain temperature also creates a really nice environment. And there's a business case for this too. It's often hard to sell these types of solutions, but this kind of granularity of information allows us to evaluate things like building costs for cooling, infrastructure costs for that cooling equipment, also water use and energy use, and turn that into real dollars. There's definitely a wellness. I talked about the mortality rates associated with heat waves. Really looking at wellness on multiple scales, your personal experience, the community, and the community exists within a larger ecological context. So some of what we're doing is understanding the modeling implications of reintroducing ecology into community and personal experiential scales, and how that may actually inform a broader set of values, including financial costs. And the outcome is sort of allows you to look at these sort of utopian visions for modern cities, and start to understand where the thresholds are. How much of this green stuff really optimizes the performance of the city? It's interesting to look at these engineering factors and climate response factors. Evapotranspiration and shade can be leveraged. Rehydrating cities so that there's available moisture to evaporate can have a dramatic impact on heat spikes. And I think it informs and reinforces some of the human values too. I mean, we're designing cities for people ultimately, and being able to connect some of these less tangible values. People seem to inherently feel like having more vegetation and life in cities is better, we're happy to be able to integrate some of these tools into a workflow that shows that it actually performs better as well. So thanks for being with us, and happy to answer any questions.